So we are seeing about RC oscillators. So one type of RC oscillator is a Wien Bridge Oscillator. Okay, so as the name indicates, it is going to use a bridge. A bridge is a network of this type. So you have four nodes, and in between the four nodes, you will have either resistance or impedance. Impedance may be inductance or capacitance. But this bridge, we are specifically taking it in such a way that two of the arms of the bridge are going to have resistance, and in one arm, I'm going to have RC series, and one arm, I'm going to have RC parallel. I think you can see it in the diagram. So this bridge is called as a lead lag network. So if RC series is going to provide a leading phase shift, RC shunt will provide a lagging phase shift. So effectively the phase shift will get cancelled when the signal comes out of the bridge. So ideally I can say this bridge is going to provide zero phase shift. That is why it is called as a lead lag network. So it is going to have a leading network in the form of series RC, and it is going to have a lagging network in terms of shunt RC. And this is going to be present in the feedback path. So you are going to have two common emitter amplifiers in cascade. So this one provides a phase shift of 180. This second one is going to provide a phase shift of 180. So the effective phase shift is going to be 180 plus 180. It is going to be 360. So my feedback path should not have any phase shift. That is why I'm going to use a lead lag network in the form of a bridge. Okay, so that is the construction of Wien Bridge Oscillator. It is very simple. I'm going to use voltage divided bias for both the common emitter amplifier. You can see the resistance R5, R6, R7, R8. Okay, they are going to form voltage divided bias. These four resistances, they are going to form voltage divided bias. And RC1 and RC2, you know, it is a corrector resistance or it will act like a load. CC is your coupling capacitance you have for both the common emitter amplifiers, and you have emitter bypass capacitance for Q2. And Q1 is connected, emitter is connected to the point D, and output is taken from collector and given as input to your bridge. And output from bridge is taken and given as input to your base. So this is the connection of your Wien bridge oscillator. So since I'm going to use a two-stage common emitter amplifier, the total phase shift is going to be 360 degrees or 0 degrees. So one condition is satisfied. And I'm going to take a balanced bridge. The balanced bridge means it is going to have zero phase shift. So it is not going to provide any additional phase shift to my network. So the network consists of a lead lag network. R1, C1 is the lead network, and R2, C2 is your lag network. So they are aided by the voltage dividers R3 and R4. So the four arms of the bridge, two arms have pure resistance and two arms are going to have resistance and capacitance in series or parallel. So the output of bridge is going to be the input to your base of transistor Q1. So see, if the bridge is going to be balanced, the bridge is perfectly balanced, means the product of opposite reactance is going to be same. So R3 into this R2 parallel to C2 will be equal to R4 into R1 plus C1. So you bridge is perfectly balanced. This is the condition. The product of impedance of the opposite arms are going to be same. So R3 into R2 parallel to 1 by j omega C2 will be equal to R4 into R1 plus 1 by j omega C1. So if the bridge is perfectly balanced, you can write this condition where XC1 and XC2 are the capacitances of the reactance of the capacitor. So if you simplify this equation and if you equate the real part and imaginary part, you will get the frequency of oscillation as not equal to 1 by 2 pi root of R1, R2, C1, C2. If you take R1 equal to R2 equal to R and C1 equal to C2 equal to C for design simplicity, then F0 will simplify to 1 by 2 pi into RC. So R3 by R4 ratio will decide how much amount of gain is required. So we will find that at the frequency of oscillation, R3 by R4 will be greater than 2. So this will be very much helpful in providing sufficiently high gain for the circuit to oscillate. And Wien bridge oscillator, you know, it's a low frequency oscillator, so it is used in commercial audio signal generation.